Hi, my name is Derek and I will explain to you about what are the catalysts. Catalysts are substances that accelerate chemical reaction without being consumed by the process. They function by providing an alternative reaction pathway with lower activation energy and making the reaction more efficient. After the reaction, catalysts remain unchanged and can be used repeatedly. And the importance of catalysts in chemical reaction is catalysts play a crucial role in reaction efficiency and sustainability, which it reduces the energy consumption, enable the selective reaction, minimizing waste, and supporting greener industrial process. It is widely applied in petrochemical industry, pharmaceutical synthesis, and environment protection technologies. Now, we jump to the real world of application of catalysts, where there is a sustainable chemistry which has palladium-based catalysts with low metal loading and recyclability with support greener synthesis. There is also having a metal organic framework (MOF), which enable reusable with low impact reaction. In the side of energy and environment, there is a nanocatalyst used in photocatalytic water to split generate green hydrogen. There is also a biogenic palladium nanoparticle which transforms the organic compound into an eco-friendly way. Lastly, the industrial waste valorization, which the catalyst help to convert waste into fuels and valuable chemicals and supporting a circular economy.
Assalamualaikum to everyone. Today I'll be talking about types of catalysts, their mechanism, and some real-life example of a chemical reaction. So we have three types of catalysts, whereas a homogeneous, heterogeneous, and enzymatic catalyst. So let's begin with the homogeneous catalyst first. These catalysts are in the same phase with the reactant, typically in a solution. So this will allow the catalyst to mix uniformly with the reactant and interact on a molecular level, leading to an efficient reaction process. A good example is the esterification of alcohol with the carboxylic acid. For instance, when the ethanol reacts with the acetic acid, the catalyst form cation hydrogen from sulfuric acid is in the same liquid phase with the reactant, so it will protonate the carboxylic acid, making it more reactive and speeding up the reactions process. So the mechanism of homogeneous catalysts include three steps. First is coordination, reaction, and regeneration. So for the first one is coordination, where the catalysts is a first bind with the reactant to form an intermediate complex. Second is the reaction, where the intermediates undergoes the rearrangement or facilitates the breaking or form of bonds. The last one is rearrangement. After the product form, the catalyst will release unchanged and ready to catalyze the next reactions. Now let's move on to a heterogeneous catalyst. These catalysts are in a different phase than the reactant because it usually in a solid, while the reactant are in a liquid or gas phase. These are the most widely used catalysts in the industrial process because it is easier to separate and reuse. So a famous example is a Haber process where the nitrogen gas reacts with the hydrogen gas to form an ammonia. So here a solid ion catalyst is used to break the strong nitrogen triple bond and allowing the reaction to proceed more easily. Mechanism of heterogeneous catalyst involve four steps. First is the adsorption, where the reactant are bind to the catalyst solid surface. Second is a reaction when the bond of the reactant are weakened and the new bond are formed on the surface. The third one is the adsorption, where the product are released from the surface. And the last one is the catalyst surface are remain active and can be reused repeatedly. Now let's take a look at enzymatic catalyst. Enzyme is a biological catalyst made of protein. They play a vital role in speeding up reaction in living organisms. So enzyme can work under a specific molecules called substrate. So for example, enzyme can convert a starch into the maltose by breaking the glycosidic bond in a long chain polysaccharides. So without enzyme, most biochemical reaction would be too slow to sustain life. So this process happens extremely efficiently and under mild conditions, like something that is difficult to achieve in a non-biological systems. Mechanism of enzymatic catalyst. There are three steps on how the enzyme works. So the first is binding, where the substrates bind to a specific region of enzyme called an active site. This form known as enzyme substrate complex. Second is the catalyst, where the enzyme helps the reaction to occur by lowering the activation energy. It does this by stabilizing the transition state, making it easier for bond to form or break. Finally, the product is released from the enzyme, which remain unchanged and is ready to catalyze another reactions. These make enzyme reusable and highly efficiently, like it can process thousands of substrate molecules just in 1 second. This entire process can repeat rapidly with high specificity, which is why the enzyme is important in biological processes like digestion, respiration, and metabolism.
Hi, my name is Patricia. So now I will start with the application in chemical reaction. So the first one we choose Haber-Bosch process, which is ammonia synthesis with the chemical equation N2 plus 2H2 that will produce 2NH3 that using iron catalyst. Iron catalyst promoted with potassium, aluminum oxide and calcium oxide that improve performance and longevity. So the description process is the reaction is carried out at a high temperature within 150 to 300 atm and a high pressure between 400 to 500 degrees Celsius. And then hydrogen is obtained from the natural gas which is methane through steam reforming, and lastly nitrogen is sourced from the air. So the role of catalyst is lower activation energy, increased reaction rate and provides active sites.
Hi everyone, now I will continue with the next two examples of catalyst application in chemical reaction. The second example is ozone decomposition in clean room and air treatment system. This process uses manganese dioxide as a heterogeneous catalyst. The reaction is carried out at room temperature and atmospheric pressure. Manganese dioxide provides active sites that allow ozone gas to break down faster into oxygen. This helps prevent ozone buildup, especially in sensitive environments like semiconductor labs. The catalyst remains solid, is not consumed and can be reused multiple times. It is effective even at low temperature, making it very efficient for environmental cleanup. The last application is acid catalyzed esterification, where sulfuric acid is used as the homogeneous catalyst. The reaction involves acetic acid and ethanol, which form ethyl acetate, a compound commonly used in fragrance and solvent. All reactants and the catalyst are in the same liquid phase. Sulfuric acid acts as a proton donor to activate the acetic acid and also help remove water from the system to shift the reaction toward ester formation. The catalyst is not consumed and can be recovered after the reaction. In conclusion, these three examples, Haber-Bosch, ozone decomposition and esterification, show how catalysts are used in different fields to improve reaction efficiency, save energy and support sustainable chemical processes.
Good morning, Doctor, and hello everyone. My name is Durkeswari Muryandi and my matrix number is CN240366. Today I will explain about future trends. First of all, emerging technologies in catalytic applications. First of all, nanocatalyst revolution. Nanocatalysts are catalysts that made of particles so small that millions of them could fit in a pinhead. Because they are small, they have larger surface area which provides more sites for reaction. They help chemical reaction happen faster and use less energy. This technology especially used in fuel cells, green energy and medicine. For photocatalytic water splitting, nanocatalysts break into H2O, which hydrogen gas and oxygen. Hydrogen gas can be used as a clean fuel. The second technology is metal organic frameworks, which is known as MOF. MOF are crystal-like structure made from metal ions connected to organic linkers forming a 3D sponge. These structures have tiny poles where the gases can be trapped. MOF can capture harmful gases like carbon dioxide. The trapped carbon dioxide can be converted into fuels or new materials. This can be reduced pollution. The trapped carbon dioxide are used by factories, where factories use MOF to capture carbon emissions before they pollute the air. The last technology is the technology we all use, which is AI, artificial intelligence in catalytic design. AI now used by scientists to predict the best possible catalysts for a specific chemical reactions. AI can process millions of chemical combinations in seconds. It also can save money and the research time. AI also leads to discover of brand new catalysts where the humans may not think. AI designed catalysts are helping industry to recycle the plastic into fuel in more effective way. Now we are going to discuss about ethical implication of catalytic usage, which the first one is fairness and global equality. Catalyst technology should not just benefit rich countries. Poorer countries should also have equal access to green technology to solve their pollution problems too. Climate change is a global problem. Technology sharing means everyone works together to save the planet. For example, using MOF to capture carbon dioxide should be available for all the countries, not just to the wealthy industries. The second one is exploitation of rare earth elements. Some catalysts are used rare and expensive metal like platinum, palladium or cobalt. These metals are often mined in developing countries. Sometimes it is dangerous or unfair in working condition. It is also unethical if the companies become rich and workers suffers. Industry need to make sure that the materials used come from in a safe and fair mining practices. For example, platinum used in car catalytic converters often mined in Africa in a unsafe environment. The last ethics is recycling catalysts. Many catalysts can be reused after the reaction, but not only recycled properly. Throwing away a valuable metals is wasteful and dangerous for the environment. Recyclers can save money, prevent pollution, and reduces the need into a new mining. For example, car catalytic converters, the old parts can be recycled or recovered to a platinum. Let's move on to the next topic, which is environmental impact of catalytic usage. The first one is pollution fighters. Catalysts help reduce harmful gases released by the factories and vehicles. For example, catalytic converters in cars break full gases into harmless ones like nitrogen and water vapor. This leads to cleaner air, healthier people, and help prevent acid rain by reducing sulfur and nitrogen oxides. The second one is energy savers. Catalyst makes reaction happen at lower temperatures, meaning less fuel is burnt and less carbon dioxide gas is released. This saves fuel and money while helping to reduce global warming. For example, in ammonia production, which uses Haber processes, catalysts help factories at lower energy use. The third one is green future, which is biomass catalyst. Scientists now creating catalysts from the natural materials like in fruit peels, coconut shells or seashells, which offering a cheaper and not toxic alternative to metal catalyst. These renewable catalysts are eco-friendly and reduce the need of mining rare metals. For example, shrimp shells can be used as catalysts in biodiesel production. Thank you.
Alright, so for the conclusion, catalysts are critical in modern chemical processes such as boosting reaction efficiency, lowering energy consumption, and promoting sustainable growth. This group project thoroughly investigated the many types of catalysts such as homogeneous, heterogeneous, and enzymatic, and their application in durable industrial and environmental settings, including the Haber-Bosch process, ozone decomposition, bioethanol generation, and esterification reaction. The use of modern catalytic technologies such as nanocatalysts, metal organic frameworks, and AI-assisted catalyst design exemplifies the gradual transition to a greener and more efficient chemical operation. Furthermore, ethical and environmental consideration emphasize the necessity of fair resource sourcing, recycling, and equitable access to green technologies around the world. Collectively, these findings highlight the catalyst's importance not just in fostering chemical innovation, but also reaching long-term sustainability targets across industries all over the world.